Okay. Let's go. So last time we introduced exponential functions and the natural exponential, the most important function in all of mathematics, don't worry. Become math majors in a few years, you'll understand. Right now, we actually want to talk about a very intimately related function. So we're going to cover 4.3 and 4. We're going to talk about logarithms. For sure they're called logs. And logarithmic functions. For short, we can call them log functions. Okay, let's start with the definition. I can say v here, because as we'll see, the logarithmic function is a one-to-one function. The logarithm of a number to a given base is the power or exponent to which the base must be raised with the number. So what are logarithms? Logarithms are powers. They're powers in a very special context. Okay? So I can talk a little bit about the notation here. It might look like something like this, log to the base a of b. Okay? So this is called log to the base a of b. That's how it's read. So this is log, short for logarithm. The base a is indicated by writing it as a subscript on the log, and the b is something that you plug into the logarithm. Logarithm you can think of as even a function like f of x, like you have log of this b, right? Now once you let that b be a variable like x, now you get a log function, which we'll talk about soon. But this is what a logarithm is. It is actually just a number. In fact, it's the power. And in fact, we can rethink of the definition. I can reword this definition as an equation. This leads us to law 1, which is pretty much the definition of the logarithm, just written more mathematically. The logarithm of a number to a given base is equal to the power to which the base must be raised to give the number. This means writing this expression is exactly the same as writing this expression. To say that the log is c means that if I take the base a raised to the power c, I will get the number b, right? So this expression means exactly the same thing as that equation. In fact, you can think of a log as rewriting this kind of equation. The log comes in when you try to solve for the power, right? So you want to make the power the subject of the formula, use what's called a logarithm, that's how it works. So we simply use this notation to refer to this idea. So let me give you an example here. Log to the base 2 of 8 is, what would you guess? 3. Because I need to take 2 raised to the power of 3 to get the number 8. So that's it. That's what a log means. Okay. Now you might say, well, we already have exponential equations. Why make it complicated? What's wrong with these math people always making things complicated? The idea is quite the opposite. Logs can actually make things a lot simpler. Let's talk about law 2. How can a log make things simpler? Well, I'm not going to prove it for you. I'm just going to actually tell you what these rules are. So this is the first rule. And by the way, all these rules you should have memorized. Okay, so that's the first rule you should have memorized. That's the definition of the logarithm. Writing this expression means that. Now, once you actually do that expression, a lot of nice things falls out of this. For example, if you have log to the base a of something to a power, you're allowed to bring that power down and multiply. So logs turn powers into multiples. And you can imagine what's going on here. If you take something to a power and raise it to another power, you multiply the powers. So exponentiation, when you look at the powers, becomes multiplication. So it actually will reduce an exponential operation to a multiplication operation, which tends to be easier in most cases. So if I say, so for example, I have log to the base 3 of x to the 5th, I can just think of this as 5 logs. Right? So instead of having to raise x to the 5th and find the log of that huge number, I can just find the log of the base of x and just multiply it by 5. So that's a very useful rule as well. Here's other ways that logs make things nicer. We know that when you multiply things of the same base, you add the powers. This tells you if you're logging something that's a multiple, it becomes a sum. This is law 3. You have log to the base a of, say, x times y. This is equal to log to the base a of x plus log to the base a of y. Logs turn products into sums. So we'll look at examples of all of these pretty soon. When it comes to division, I know if I divide things of the same base, I subtract the powers. In other words, if I take log of a division, it just becomes a subtraction of logs. So logs turn products into sums, they turn divisions into subtractions. There's law 5. This law has a name. It's called the change of base formula. This is a rule that tells you how you can change the base of a logarithm, which is super important, and I'll mention why it's important a little bit later, and we'll do some examples. It says if I have log to the base a of b, I can actually write that as log to the base c of b divided by log to the base c of a. This works if your a is not equal to 1. I'll explain why in a bit. But that is a formula that allows you to change the base. So let's say you're working with a logarithm in base a. You don't like base a. You can introduce a base of your choosing, base c. Right? I can introduce a convenient base, which I call base c, and I can introduce a new base by this formula. For example, let me show you an example of why you might want to do something like that. So actually what was log to the base 2 of 8? You guys all said 3. Was easy to actually see what that answer is, what that answer was 3. What if I asked you, what was log to the base 4 of 8? Okay. Not so easily answered, is it? Right? Now, here you immediately get into trouble. 4 raised to the first power is 4. 4 raised to the second power is 16. You overshot your target. So the answer is obviously between 1 and 2, but what exactly is it? Is it halfway between 1 and 2, exactly halfway? Is it 1.5? Is it 1.7? 1 point something else? Right? So here, it turns out that 4 is an inconvenient base for you. It's not easy to say what the answer is right off the bat. However, there is a base that would be more convenient for both of these numbers, like
2.
Base 2. I know what 4 is as base 2, and I know what 8 is as base 2. So 2 is a very convenient base for me to work with these particular numbers. And I can therefore introduce this base via this formula. So I can say this is equal to log to the base 2 of 8 divided by log to the base 2 of 4. Now what's log to the base 2 of 8? 3. Log to the base 2 of 4? 2. So the answer is 3 over 2. Exactly 1.5, it happens to be in this case. And of course you can check this. If you take 4 raised to the 3 over 2 power, remember what that means. That's just the square root of 4 cubed by our exponential rules. That's 2 cubed, which is 8. So yeah, 4 raised to that power gives me 8. Therefore, log to the base 8 of 4 is 3 over 2. So this formula allows me to work in virtually any base I want, any base that's convenient, and usually it's going to be a nice base. I'm going to explain more about that in a bit later. But that's how here's one simple example of where something like this might come in handy. Now, these laws are the really important laws. You have to know these, no excuse. The laws I'm about to tell you, there are about 10 laws in total. The laws I'm about to tell you, technically you can derive them from these, but I don't want you to actually waste your time doing that. I'd rather you guys just memorize them and just know them right off the bat. Okay? So, let's look at another law. Law 6. Log to the base a of 1 is 0. Right? Now she thought about that through the log rule. She's thinking, what do I have to raise a to in order to get 1? Oh yeah, there's an exponential rule that says x to the 0 is 1, as long as x itself is in 0. So yeah, log of 1 is 0. It's always 0, no matter what the base a is, right? Here I'm putting a can be any number. Normally for a logarithm, we assume a is greater than 1. But I'll talk about that in a little bit. Log to the base a of 1. Once you make a construction that can be written as a logarithm, if you plug 1 into that thing, 0 is going to be the output. Because 0 is the only number that you can take any non-zero number to, raise to the 0, it will give you 1. Right? But that's just something you should just know. Log of 1 is 0. Doesn't matter what base I'm working in, log of 1 is always 0. Law 7. Okay. What about this one? What would be log of 0? 1. A raised to the power 1 gives you 0. No. What do you think it is? You can even pick a specific number if you want. So say it's log to the base 2 of 0. What power should you raise 2 to in order to get 0 as the result? 2 to the 0 is 1. What number can I put here to get 0?
Is it undefined?
It's undefined. There is no such number. That's going to be important when we're figuring out the domain of a logarithmic function. Knowing that you can't log 0 is going to hint to you where the domain is. We'll get to that pretty soon. Right, if I have a non-zero number, there is no power I can raise it to get 0 as a result. Therefore, log of 0 is not defined. It is not an answer, right? If you got log of 0 as an answer, either you made a mistake or the problem you're working on has no solution. You need to be aware of that. So the same way you can't take the radical of a negative number, you can't take the log of 0. It's just it makes no sense to actually do that. In fact, if you assume a is a positive number, you also can't take the log of a negative number, right? Because there's no power you can raise a positive number to in order to get a negative one. So we'll talk about that soon. So you should know log of 1 is always going to be 0. Log of 0 is always undefined. It'll never work for any base. Let's look at law 8. It's almost obvious, but it's worth actually knowing specifically. If I take log to the base a of an exponential that looks like a to the x, what is that answer? What power do I have to raise a to in order to obtain a to the x? X. Log to the base a of a to the x is always going to be x. Right? So if I say, what's log to the base 2 of 2 to the 7? 7. What's log to the base 3 of 3 to the 9th? 9. What's log to the base 4 of 4 raised to the pi'th power? Oh, I don't know, confusing. No, it's pi, right? Log to the base a of a to the x is always x. Follows straight from the definition. This one is not as obvious. The proof isn't long, but I don't really want to do it. Pretty much you undo the logarithm and retake a logarithm in a very convenient way, and you'll obtain the opposite one is also in effect. If you take a, and in its power you put log to the base a of x, it turns out that that is also x. So this kind of relationship works in the opposite way as well. So if I have 2 raised to the log to the base 2 of 3, the answer is just 3. Just forget it. It's like the a and the log a can cancel, right? Which you kind of see here, like the a and the log a can cancel. We'll talk a little bit more about that pretty soon. But this is another law. It's good to just know. I always call this law 10. Not really a law. It's more of a notational thing. So obviously logs and exponentials are intimately acquainted. A log equation is just another way to write down an exponential equation. And last time I told you about one of the most important kinds of exponentials. So let's actually talk about what that guy looks like. So if I have log to the base e was that number that we defined in the previous class. What do we call that? Well, I'll just tell you, it's a notation. It's not something you figure out, it's just something you just know because of convention. We call this ln. Okay. So even on your handouts, you see all these things where it says like ln2, that's the guy, that's what it's talking about. Okay. When the base is e, we call it ln, lnx, people often call it affectionately. And this guy has a name, it's called the natural log. Right? Why? Its base is the natural exponential. So that's just a name for this. And I want you to be aware that all the above rules that I mentioned will work for this guy. So let me just make a note of that. So for example, if I have ln of a equals b, what it means is e to the b is equal to a. Right? I can take the base, which is e, even though it's not, you can't see it, raised to the power b, it should give me the number a. And if I have, say, ln of e to the something, it just gives me the something. If I have e to the ln of something, it just gives me the something. Right? If I have ln of x times y, it's ln of x plus ln of y, etc. All the rules that I mentioned works for logs will work here. It's just another log, right? So don't be confused. All the log rules, as mentioned, apply to this guy. We just write this when we're thinking of a very specific base. Base e gives us this notation. We call it ln. It's a notational thing. So, in the same way that the natural exponential is the most important exponential function, in that way, the natural log is the most important logarithm. And normally, and here's where I can do my plug about the change of base formula, because people usually don't like telling you about this. Normally, if you're working in any other base in a calculus context that's sufficiently complicated, you want to work in ln. So if you have a problem in any other base, you want to change it to ln, you would use the change of base formula. ln is where it's at. ln is what you want to work with. Any mathematician is going to work with the natural log and not care about any other log. Anytime they get anything in any other base, they're going to change it to base e, because that's the most convenient thing to use. It's the natural thing to use. That being said, most people at this level are not set out to be mathematicians. So we have what we call the common log, the log of the people, not the mathematicians.
Yeah.
And this just means when you write log x and you don't specify the base, what does that mean?
Base 10.
Base 10. Right? Log of the people who count on 10 fingers. Right? So what engineers use. You have to count on their fingers. You can't count E on your fingers, but math people don't care. We use it because it's convenient. Right? And it's worth mentioning, like when you become highly specialized in some field, this log is going to take on the base that's important for your field. So there are some books, just to warn those of you in a few years' time, that when they write log x, they really mean ln, because they're like, the natural thing to use is base e. Why would we even think of base 10, right? So if you look in Wolfram Alpha, for example, and you type in, you're checking your work with something, so that's another reason why I want to tell you this. You're checking your work with something, whenever Wolfram Alpha tells you log x, it actually means base e. Don't be confused by that. I'm just telling you, because when you become specialized, this guy, the common log, just becomes the log that is good for your specialty. If you're a computer scientist, log x would mean base 2, because they work in binary. Right? So they do everything in binary, base 2 is convenient for a computer scientist. So eventually, if the base isn't specified, a computer scientist would assume it's base 2. If it's not specified, an engineer would assume it's base 10. If it's not specified, a mathematician would assume it's base E. But at this level, we define this guy to be base E, and without any designation, we call it base 10. Because you're more likely to be an engineer than you are to be a mathematician at this point. So we'll call that the common log. Whenever I don't specify the base, it means base 10. If I want to emphasize that the base is E, I will write ln, and that's called a natural log. So those are all the log rules. That's kind of what logs are. Now, let's talk about log functions. Where was the last place I wrote it? Okay, sorry. We'll do some computational examples at the end. I just want to fully develop what a logarithm is. This is how it would work with computations, but what is it as a function? That's what I'm going to talk about now. Log functions. So, these are functions of the form, they look like this. Y equals log to the base A of x, right? Where x is a variable. It's your independent variable. We spoke about that when talking about functions. That's your input, and it changes. And A, which is normally considered to be greater than 1, is a constant. Right? That gives rise to this kind of function. I want to show you what would this function look like. But we're not going to do it by plotting points because that's beneath us now. It's very high school to plot points. Let's look at the graph. And of course, you can do transformations of this. You can multiply by a number, you can add a constant to shift it up. It's a function like every other function. All the rules I tell you about functions will apply to this guy. Except, of course, certain things you can't plug in. So we'll talk about that right now. So when we're looking at its graph, if you want to figure out what it is, consider laws 8 and 9. What do they tell us? Like if you were to look at law 8 and 9. Summarize in a phrase what those two laws say. Yeah?
They're inverse functions.
They're inverses of each other. remember we looked at what inverse functions and we said, okay, if you take f of g of x, you get x, and if you take g of f of x, you get x. Well, if you take f to be log, and you take g to be a to the x, you will notice that f of g actually looks like, and we know that that is x. The g of f means I would take f and plug it into the x where the g is. That would look like, and we also know that's x. So these rules, the fact that these two things give us x, means something like this happens, which by definition it means they're inverse functions. Knowing that they're inverse functions, what does this tell us about the graph? Well, what does the graph of an exponential look like? Like if I wanted to graph y equals a to the x, it goes like this. So it goes like this. Right, we looked at that last time. We showed that it actually increases faster than any polynomial to any power. It's a very different animal compared to any function that we've seen before. At this point in our mathematical journey, that is the fastest growing function we know about. Now, how do you obtain the graph of an inverse function if you know the graph of the function?
You reflect it over the
Reflect over y equals x. You're going to look at the line y equals x. It's not a part of the graph, so I'm going to draw it broken. And I'm going to take the mirror image. Now, this guy passes through 1, of course, because a to the 0 is equal to 1. And by the same token, log of 1 is going to be 0. So this guy is going to pass through 1 over here because it's a reflection. And that's what the graph of log base a looks like. So we don't need to plot points, we know that shape. So that's the graph. So if you look at a log graph, a is a positive constant, bigger than 1, it looks like that. It will pass through 1. And so that's the basic shape. Kind of like how you know a parabola looks like this, a log looks like that. That's the basic shape. And this is the basic shape of an exponential. Of course, we can swap it and stretch it and shrink it and move it up and down and flip it using transformations, but that's the basic shape. This is the quintessential exponential. This is the quintessential logarithm. Of course, just to be, we can do transformations just to make you understand. So if I were to look at y equals minus log to the base a, just to emphasize that it's just another function, that means you would reflect in the x-axis. So that would look like this. If you look at y equals log to the base a of minus x, well, that's a reflection in the y-axis. So I'm going to take this and flip it over here. If you look at minus log of minus x, then I flip this one in the y-axis. Look like that. Right? And of course, if I plus something, it's going to shift it up. If I add something to the x, it's going to shift it to the left. If I subtract something from the x, it's going to shift it to the right. All the transformations apply. Knowing how to graph logarithms and exponentials is actually something important. So it always shows up on a final. You'll have one problem that's going to ask you to graph either one of these guys, so you have to be prepared to graph both. So we'll do some examples of that afterwards. So just know all the transformation rules apply. In the usual way. Very common issue with mathematics is that a lot of students get confused by notation. Right? They see a square root, oh, they freak out. They see pi in a weird position, they freak out. Right? In the same way, a lot of students, when they see a log or an exponential, they freak out. They don't know how to deal with it. Right? You deal with the way we deal with everything. Right? Mathematics is very abstract. When we tell you the rules work for f of x, we mean it works for every such f of x. Add 1 to x, it means you shift to the left of 1. It doesn't matter what the f itself looks like. Right? So don't get scared by the actual details. Think in general, right? You'll deal with this function in terms of transformations like any other function. Let us talk about, which I don't believe I did this for the exponential, so I'll also do it there. For this, at the moment, let's talk about the domain and ranges of these graphs. And by the way, the fact that they're inverses kind of makes that idea pretty easy to apply, because inverse functions switch the x and y. So what that means is the domain of a function is actually the range of its inverse, and the range of a function is the domain of its inverse. So if you figure out the details for one of them, you automatically know the details for the other one. So that's a very helpful tip, to just know a logarithm is an inverse of an exponential. That will tell you a lot of details and a lot of useful information about the logarithm. So sometimes if you're ever wondering how the log behave here, you can kind of ask yourself how the exponential behave, and then you kind of reflect that relationship. Just talk about the domains and ranges. Let's start with the exponential. Y equals a to the x. Let's say our a is greater than 1. The graph is going to look like that. X. What is the domain of f? And what is the range of f? Versus, let's say g of x is the logarithm. A is greater than 1. Just like that. What is the domain of g? What is the range of g? And yes, this is something that you will specifically be asked for, so you need to know how to talk about this. So the exponential, what's the domain? All real numbers. You'll notice that no matter where we go on the x-axis, plug in this x, I will be able to track it and find a y, no matter where I am on the x-axis. The domain is actually all real numbers. I can plug in anything into the exponential and it will work. It will give me a meaningful number. Whether I put something positive or negative or 0, it will have to give me a number. And so the domain is all real numbers. By the way, that automatically means that the range of this guy is all real numbers. And you can actually see that here. The same relationship happens with the y-axis. No matter which y I'm thinking of, there's going to be some x that gives me that y. Even if I think of a negative y, there's going to be some x that gives me that y. Right? The range here is going to be everything. All y values, all output values along the y-axis will be obtained because all x values for its inverse are usable. What is the range of the exponential?
0 to infinity.
So this?
No. No. Open.
0 is not included, right? It never actually touches the x-axis. It never becomes 0. An exponential, a to the x, when your base is positive, is always itself a positive number. So that kind of tells you the domain of this guy is going to be the same, 0 to infinity. And you can see that it never actually touches x equals 0, but it's good for x above 0. Now, there's a term we use to describe this behavior. This idea of approaching some line but never actually touching it. Does anyone know what that's called?
The asymptote.
It's called an asymptote. So here, you should note y equals 0 is an asymptote. For f of x equals a to the x. So it has what we call a horizontal asymptote because it's a horizontal line. There are other kinds of asymptotes. An asymptote can actually be a curve, but in this case they are actually straight lines. And x equals 0 is an asymptote for the log graph. So logarithms will have vertical asymptotes. Also something they tend to ask you, I don't really want to go too much into asymptotes now, but for us, not the best way to think about it, but in pre-calc it's okay for you to think about it this way for now. So for us, an asymptote is a curve that basically what an asymptote is. You'll notice here I can call 0 an asymptote because as the x coordinate goes to negative infinity, we approach y equals 0. I can call x equals 0 an asymptote because as the y coordinate approaches negative infinity, we approach the curve y equals 0. So as one of the coordinates are approaching infinity, if there's a line that your graph is getting closer and closer to, we call that an asymptote. I wouldn't really worry about it more than there. We only need to know about asymptotes in specific instances. This is one of them. They'll specifically ask you about asymptotes for exponentials and logarithms. This can also tell you something. So sometimes we might have a transformation of a logarithm. So it's not just x that's important, right? So if you were to say, what about, say, log to the base 2 of x minus 1. Where is that asymptote? So let's see if you guys see it and then I'll actually tell you about it. Yeah?
Maybe x equal 1.
Explain.
because that's like transformation basically, so it's going to shift over to the...
Right. You can think of it in terms of a transformation. This just means a shift to 1, just like it would mean for any other function, right? So that means I shift this graph over 1 unit to the right. So now the asymptote that was at 0 now shifts over to 1. You can also find that location by figuring out where the log would be undefined. Notice that if I had set this equal to 0, x equals 1 would be the answer, right? And remember, log of 0 is undefined. That's going to be the guy that we can't touch, right? So your log is going to be like going towards, can't touch it, right? Your log is like has to avoid that line. It cannot touch the 0. So there are a couple ways you can think about it. You can just think about it purely as a transformation. So, oh, x minus 1 means shift to the right 1. Or you can just realize that if I set the inside equal to 0, that's the line we cannot touch. That's going to create an asymptote. So let's actually write that down. And similarly, what about an exponential? Then I'll write it down in some detail. Let's look at something like y equals e to the 3x plus 1. This has an asymptote. Let's put -1 just to shake things up. So this has an asymptote at x equals 1. Or asymptote of x equals 1. Where would you say this one's asymptote is?
Let's see.
Hmm?
0?
0? What? Oh, you have to be specific.
Um,
Because saying, for example, y equals 0 versus x equals 0, these are two very different things, right? That's a vertical line, that's a horizontal line. So when you say 0, which 0 are you talking about?
I would say y equals 0. I mean x equals 0.
So it has a vertical asymptote, this guy?
Yeah.
Well, let's think about it. What about y equals e to the 3x? What does that look like?
That would be is an exponential function.
It's an
so
exponential, so what does it look like? And
it'll
the base
go,
is 2 point something, so it's definitely bigger than 1. Yeah, so it's going to look like this. Okay, so if I looked at that guy and then I did -1, what's going to happen?
It's gonna go down. +1 for y equals 1.
Well, what does, when I say -1, what does that do?
It's gonna go down.
It shifts it down, right? So this guy's going to go, it's going to drop down by 1 unit. Now what's going to be this new line here? Y equals -1. There's another way I want to show you how to do this one, but you kind of need to know how to solve it. Yeah, I'll tell you something else later that will make this easy. For now, just think of this in terms of transformations. We have to look at solving log and exponential equations before I tell you the easy later on. It's not as easy as just, oh, just set this equal to 0. What you could think of it as is just knowing that this part has to be greater than or equal to 0, well, greater than 0, which means as a whole, this whole thing needs to be greater than -1, which means it has to be above 1. That's another way you can think about it in terms of inequalities. But we can actually solve for that? Pretty much figuring out where that would be 0 is going to be the guy that is going to create the asymptote. But we probably don't know how to solve that yet. I haven't really spoken about it. So for now, just think of it in terms of transformations. Let me just state this specifically though. Okay, so if so let's look at the asymptote. The asymptote. So say you have log to the base a of, the only case we'll care about is actually linear. So let's call this mx plus b. Is the solution. And this could be plus or minus any constant and multiplied by any constant here. You can, this will not change under transformations, right? So pretty much it's the solution to mx plus b equals 0. In other words, your x is going to be, depending on what your b is, it's going to be that guy, right? So pretty much if you want to find the asymptote for a logarithm, set the inside of the log equal to 0. We know that's the line it cannot touch. And this is a very specific case, but it's the only case that you care about in pre-calc. So I'm not going to make it any more complicated than you need to know. If you want to look at something like an exponential raised to mx plus b, say plus c. And let's put here.
X equals negative b over n.
Is
The one on top?
Well, we can think of this in the following way. Okay, so here I have an exponential. I can do all sorts of things in the power. That's going to affect it horizontally. And the asymptote is horizontal. So these guys here, playing around with the power is not going to change this asymptote. Playing around with the power is going to be shifting things horizontally or flipping them horizontally. So this guy is going to remain the same. So changing the power is not going to change the asymptote. What if I multiply it by a number? Well, it's going to stretch it vertically. Now if the number is positive, it's still not going to make it past this line. If the number is negative, it will literally flip it over this line. That also is not going to affect the asymptote. The only guy that's going to affect the asymptote is this guy. Anything that makes a vertical change is what's going to affect the asymptote, right? So the only way you cannot have this as the asymptote is if you take this entire graph and shift it down, or shift it up, right? And so it's pretty much this plus c that's going to tell you where the asymptote is for the exponential function. There are other ways to think about it, but that's the easy way, I guess, in this specific case. Just look at the actual number that we added, right? So we started with something that is greater than 0, and we shifted it down by -1. So the new asymptote now is -1. If I put a +1 here, that means I would shift this up by +1. The asymptote would be equals 1, right? So those are some things in general. They'll specifically ask you this kind of question on a final, so at this point you can just know about that. We'll get used to the idea more when we learn to solve some equations. So these are actually important ideas to know. So to figure out where the asymptote will occur for a logarithm, set the inside of the log equal to 0. And to figure out asymptote of this guy, as long as your power isn't something that makes it not an exponential anymore, you just look at the vertical shifts. Is that all I want to say? say about graphs. Domain, ranges, and asymptotes. Yes, I think that's all I wanted to say about. Well, not quite. Do I want to do that now? Let's do it now. Let's do it now. I'll do those examples. Since we're here, we're dealing with graphs anyway. I'm going to skip to my graphing examples, even though I didn't have them right now. So let's look at some graphing examples. I'm going to keep them pretty close to the kind of thing you'd be tested on. So if you go into your homework, you want extra practice, you're going to pick problems roughly similar to the one I'm asking you now. So it'll say something like, identify the domain and range find the intercepts and asymptotes and sketch the graphs. So you just say sketch the graph and it'll give you an example and you're going to actually do this. And usually it's going to require you to indicate asymptotes and intercepts on your graph. So there are many ways you can ask this question, but basically this is going to be the kind of thing you're asking. You're going to be asked. So A, I'll give you a bunch of problem types. So they might ask you a graph y equals log to the base 3 of x minus 1 minus 2. E, y equals 2 minus log to the base 2. 1 minus x. C, y equals 1 minus e to the x plus 1. D, let's learn another problem here. Do the above for the inverses of A and B. So those are our graphing examples. So I've seen them ask problems of this type. So they might ask you to graph some kind of log graph, or they might ask you to graph some kind of exponential graph. Oftentimes they'll of course ask you to find an inverse of a function and graph the inverse. So this kind of takes care of all of those different scenarios. So you won't have one problem that's asking you all of this. The problem would just say this, and then it'll ask you one specific one. Right? But let's just go through a few of these just to get the hang of it. Okay, so let's start at the beginning. Domain. What's the domain here?
Is it x cannot equal 2?
X cannot equal 2?
I'm guessing.
Yeah, but why? Why would that be a guess? What prevents a log from working? Yeah?
I know that would be like a vertical asymptote.
Where?
At 1.
At 1? Okay. But where would the graph be otherwise then? What are the inputs that are allowed?
So like the domain you're asking for?
I'm asking for the domain.
So negative.
Which, if it wasn't clear before, which it probably wasn't, let me just state this specifically. Probably the nice way you want to think of it as the domain of, say, log of some function is all real x such that that function is strictly greater than 0, right? It can't be 0 and it can't be negative. Right? Because here the base is 3. What can I raise 3 to in order to get a negative number? Nothing. What can I raise 3 to in order to get 0? Nothing. Right? The only results that will work is when the inside is a positive number. Right? So when I said the domain of log x was 0 to infinity, what I really did was I set x greater than 0. So that being said, what will be the domain here? Yeah? Right, so now it's going to be not including the 1, because if you plug in 1, you get 0, which we know is undefined. But anything larger than 1 is going to be the domain. What about the range? All real numbers. Right? So we know vertically speaking, the log is going to cover everybody. Okay, so that's the domain and the range. What else? Intercepts. So what if I want to find the x-intercepts? What do we do? How do you find x-intercepts?
Make all the lines.
Right. How you always find it every single time. You set y equals 0, you want to solve for x.
That says is all real x.
So this means you're going to need this to be true,
For a.
which means you're going to need log to the base 3 of x minus 1 to equal 2 by bringing the 2 over. Okay, now how can I solve this equation? Yeah,
Could you do like the base answer exponent thing, right?
okay, so
So it'd be like 3 to the power of 2 equals x minus 1.
exactly, right? Remember what this statement means. It means if I take this base raised to that power, I get this number. So this basically means that 3 to the power of 2 is going to give me the x minus 1. Why? Well, law 1. Right? That's why it's important to know the laws. You need to know the rules. So basically here, I get my x would be equal to 10. That's going to be the x-intercept. What about the y-intercept? Here you have to set the x equals 0. But we know that's not in the domain. Our x has to be bigger than 1 here. So that means no y-intercept. So this graph will touch the x-axis at 10. It will not touch the y-axis at all. So now, we're just going to draw a graph that has those,
Professor,
yes.
what does that say? Does it says is all real x SITH?
It's short for such that.
Oh.
So the domain here is where the inside is greater than 0, so all x greater than 1. The range is going to be everything, because the log goes all the way down to negative infinity and all the way up to positive infinity. And the intercepts, you find them exactly the same way you find everything else. The log laws, or the log rules are going to help you with that. And the y-intercept you get by, again, as always, setting x equals 0, solving for y. However, you can't plug in x equals 0 in this case, so it means there's no such solution. Now, remember what the basic quintessential log graph looks like? I know the shape of this guy has to look like, well, it looks like this, right? It has to look like that. So now I know I'm just going to draw this shape passing through these points. So ultimately now when I get the graph, I would draw this. I would put in the asymptote. So let's make this red. So this is the guy we cannot touch because that gives us log of 0. I would put in my x-intercept, which is of course 10. And then what I would do, well, I would draw the shape of the log graph. So it's going to look like that. So that's my graph. Questions? So we're putting together a lot of previous ideas, obviously. Right? You need to remember how to find intercepts. Know how to solve equations, but that's from the new laws that I'm just giving you. And of course, as a principle, whenever you have a function, you always want to know what is the kind of standard shape that you should be sketching. So you know, if you saw quadratic, you're thinking of either this or that. With logs, it's the same idea. The shape looks like this. So I'm going to draw that shape. Let's do another one. You need to do them until we're sick of doing them. Remember, that's how you get better, the frustration. You want to find it. If you're practicing something you're not frustrated, you didn't go hard enough. Do it till you're just tired of doing it. I'm just, oh God, if I do another log problem for the rest of my life. I'm still getting them right though, so. If I do another log problem in my life, I'll get it right, but I wouldn't enjoy it. That's where you want to be. Get it right, but I get very bored getting it right. That's how you know you're ready. Not because, oh, I read the solution and it makes sense. I'm ready. Oh yeah, I understand what Javon did in class. I'm ready. That's not how you know you're ready. When you can get a problem right 10 times in a row, and you're just bored, and you're sick of it, that's when you're ready. You can do it without thinking about it, and the fact that you have to do it, even though you don't have to think about it, pisses you off, that's when you're ready. Why do I have to do this? Let's keep going. Domain.
Is it 1 to infinity again?
No.
Is it negative 1?
No. Are we just guessing? What's the rule? Huh?
Zero cannot be negative.
Oh, negative.
Take the inside, you set it greater than 0. This is always the rule. So I'm going to take 1 minus x, I'm going to set it greater than 0. This means that my x must be less than 1. So in other words, it's from negative infinity up to 1. That's my domain.
I just said that.
What?
I just said that.
When?
A minute ago, literally negative infinity to 1. I just said that.
It's okay.
I didn't.
It's okay.
Yeah, it's okay. Honestly, I didn't hear it because I would have written it down. I heard people say -1. I didn't hear anyone say negative being 1. So that's the domain. What's the range? Hmm? Okay. What about the intercepts? Find the x-intercept. How do we do that? So y equals 0. Solve for x. How would you solve for x? Huh? Yeah, or move the log over. I think I'd prefer to do that. How do you solve that?
2 squared equal 1 minus.
So x equals? Huh? Well, you bring the x over here, you subtract that, so it's 1 minus 4. So it's minus 3. What about the y-intercept? Right, you said x equals 0. Do we have a solution here? Yes, I can plug in x equals 0. 0 is in that domain. So if I plug in x equals 0, I would get y is equal to 2 minus log to the base 2 of 1 minus x when x is 0 is 1. What is log of 1? Log of 1 is always 0. Okay, you need to know that. It means y equals 2 is your y-intercept. So now you're going to go over here. You're going to draw the shape of a log going through those 2 points. So again, x equals 1 is the asymptote. I know my x-intercept is minus 3. And I know my y-intercept is 2. So the graph is going to look like what the log should look like. That's the asymptote, and it should go like that. Should pass through those 2 points and look kind of like that. Okay, so as an example, here's where something like a misunderstanding can happen. So remember when I was asking you guys this, I didn't hear Roberto, I was asking you guys this, and you guys were just throwing out guesses, right? And you guys got it wrong. Okay, so let's say you're doing that, right? You're doing your homework, you're practicing poems, right? And you look at a problem and you make a guess. Okay, it's minus 1. And then you kind of do it, you check your answer, the answer is wrong. Then you look at the solution and then you see what the solutions say, and they're like, oh yeah, duh. All right, okay, I get it now. You don't get it. That's very important. A lot of people are going to do that, and they're going to say, okay, I got it now, let me move on. Do not move on. The moment you guess and you don't get it wrong, I don't care how many solutions you get, I don't care how many times someone explains it to you, and you, oh yeah, I understand now that you explained it to me. You do not understand until you can routinely get the problems correct by yourself. If you have to look at solutions to know you're correct, you are not ready. Okay? Because again, that would be the comfortable thing to do, to just be able to look at it, okay, I get it, and not have to do any work. That's the comfortable thing. You don't want to do the comfortable thing. You want to be like, okay, I was wrong, I think I need to do 10 more problems. And some people might say, well, I only have 2 more problems in my homework. I wouldn't want to do 10 more problems. That's exactly why you have to do it. Are you guys getting what I was trying to say in my speech yesterday?
Yes.
That's what I'm trying to tell you, right? Because a lot of you will think that you know something, but you really don't, because you didn't fix your understanding. You just saw something in hindsight. Really where your understanding is where your initial guesses are. right? So the fact that you guessed -1 in the first place, that's your understanding. Just because someone explains something to you, oh yeah, I get it now, in hindsight, it doesn't mean you understand. You understand when you never guess the wrong answer in the first place. That's when you understand. You can get the right answer routinely. It's not a problem. I don't need to look at solutions. That's the answer. I can do 10 of them in a row, be absolutely bored while I'm doing it, and look, whenever I look at the answer, it's the right answer. The moment you get something wrong and you have to go to somewhere else for help, you do not understand. Do not look at that thing and tell yourself, oh, I understand now, and put it down. Okay? You need to find the discomfort, find the frustration. If you do that 15 times, and you guess the wrong answer 15 times, it's easy for you to tell yourself by reading the solutions, okay, I get it now. But you won't be uncomfortable doing 15 more and getting all of those right in a row. And if you do it 15 more times and you guess the wrong answer once, you know what's uncomfortable? Doing 15 more. And if you get the wrong answer again in any of those 15, and you know what's uncomfortable? I don't have any more problems in the book, now I'm going to have to find another book. I'm going to look up online for new problems. I'm going to do 15 more. When you get all 15 of those right, I'm ready. Then you move on. Find the discomfort. Do what you don't want to do. That's when you understand. If you don't hit that point, you do not understand. If you don't hit that point, it's going to be super easy for me to confuse you in a test. Like, with weird wording. He worded the problems incorrectly. These problems are hard. They're not hard. You just didn't understand. You thought you did. So yesterday when I was talking about not being comfortable and how getting better means you're not comfortable, that's kind of what I was talking about. The moment you get help from anywhere, it means you don't understand. Let's try, what was the other one? C. Okay, domain. Huh? What? All real numbers. Range. This one's not that easy because it kind of flipped on me, multiplied by a negative. What does that mean? It's a reflection. So originally the e to the x plus 1 is the guy that's going to look like this. But then once you put the negative in front of that, it now looks like this. So you're going to find that basic number, which here, of course, is going to be 1. But you know you're not above that, you have to be below that because you did the flip. So the range here should be everything up to 1. What about the intercepts? X-intercept. How do you find the x-intercept?
Set y equal to 0?
Right. That's always how you find the x-intercept. In all situations, that's how you find it. Right? So if you have a weird-looking function, how do I find the x-intercept? It's always the same way. Set y equals 0. Right? Doesn't matter what the function looks like. Set y equals 0, solve for x. How do you solve that? Right, move this to the other side. How do you solve that? Well, we have to check a couple ways. The fact that this is a 1 means it's kind of easy. If you have e and you raise it to a power to get 1, what does the answer have to be? What power do I raise e to in order to get 1? 0. It means the x plus 1 must be equal to 0. There's another way you can do it, but I'll actually save that for some future example. So if you don't get that, don't worry about it too much at the moment. So this means my x is equal to minus 1. How do you find y-intercepts? Is that x equals 0? This means your y would be equal to 1 minus e to the 1. So it's 1 minus e, right? So it's 1 minus 2.7-ish, right? So it's roughly minus 1.7-ish. If you wanted to judge where that is. And so from this I know that the asymptote occurs at 1, because that's the y value cutoff. The y values do not go above 1. So y equals 1 is the cutoff. I am going to be there or below. I know I need to pass through x equals minus 1 and y equals y is going to be what? Negative also? Pick a random number. I'm going to grab this. So remember, originally your graph looked like this. You flipped it upside down, and then you did a shift to the left. And so that's what it's going to look like. Okay, so you have, if you look in the finals, well, don't look at them yet until I actually tell you guys to start reviewing for the test. But eventually you look at the finals, you'll see they have problems like these. So this is a very standard kind of problem to ask. Like a B, or C is a very standard problem. And again, time-wise, I forgot time-wise, but I can check easily. Yeah, so time-wise, you should be doing about 6 minutes per problem on the Math 195 final. So that's another thing, right? So now let's say you're in that situation where you did like 50 of these problems already. And eventually you start getting them right. You get them right consistently. If you're taking longer than 6 minutes, you know what you have to do? Do 20 more, do 15 more. Keep doing them until you can do them in less than 6 minutes. Right? So that's the kind of mindset you want to have here. And yes, as I said, it's going to be uncomfortable in the beginning. It's going to take longer, but trust me, eventually you're going to become a different person. Your brain is going to adapt to this kind of thinking. And it's going to take you less and less time over time. And you're going to be more adept over time. You're going to be able to see things that you couldn't see before suddenly. So sometimes you're looking at you're studying with in your study group with your smart friend. You know, how did he figure that out? How did he see that? That's exactly how he figured it out. He kept pushing himself till his brain was forced to change and forced to see things that he didn't see before. Things that you didn't see because you didn't put in the work yet. It's not because he's smarter than you. He's just more experienced. He's outworking you, I promise you. People think you have all these people walking around like Good Will Hunting. You guys know that movie, Good Will Hunting? Yeah. People think that people who are good at math are like him, Good Will Hunting. They just see it, I don't know. Like everyone's like freaked out about how smart this kid is. I've been teaching for 10 years. I've been a math student for over 10 years. And I've met a lot of smart people in my life. People like that are very rare. I've never actually met one. And I've met some very smart people. Everyone I know who's like super intelligent, where I'm awestruck, they outwork me all the time. None of them just know something new the first time they see it. It comes from effort, not intelligence. It comes from them pushing themselves. I'm not saying people like that don't exist, but they're rare. You'll probably never meet one. They'll probably never be in your circles. They're probably working in the NSA somewhere. You never actually encounter them in your life. So yeah, that kid who's smarter than you in class is not more intelligent than you. He's working harder than you. He works until his brain knows how to think about that, and to the point where he doesn't have to think about it. So that's where you want to push. You want to push until you can do it without thinking about it. And getting there initially, it's going to be uncomfortable. Because you're going to have to hold yourself to that high standard. You're going to have to hold yourself to the standard of, I'm not satisfied by just reading a solution and understanding it. No, I need to make sure I can do it on my own. And that's harder. That's hard work. But that's what it takes. But like anything else, you become adept at it. You become better at doing that over time. So this is actually a nice segue into the next thing we want to do. I'm going to want to talk about exponential and log equation next. So practicing finding the inverse is probably going to be good. Does everyone here drive?
Sadly,
Does anyone here drive? Okay. Well, they can tell you. You remember the first time you learned how to drive? How crappy you were? And now you can drive with like a burger in one hand, brushing your hair with the other hand, drinking a Coke? Yeah. When you first drove, your hands are 10 and 2, you're like, so information overload. You mean I have to look in these 3 mirrors all at once? Now you have people driving, they have their foot up on the dashboard, they're like, driving with one hand. How do they do that? Because they're in a situation where they force themselves to do that thing all over. Your brain adapts. Your brain literally rewires itself. So I know right now you might think, how could I possibly do what Javon is asking me to do? If you keep at it, it's going to happen. Your brain is going to rearrange itself, I'm telling you. It's going to work like magic. You're going to be like, no, you think I'm too smart, Javon. There's no way I can do that. I got a 40 on the test. There's no way I can do that. You're just not exposed enough. In the same way that you could be a horrible driver on day 1, but if you drive consistently for 3 months' time or whatever, like depends on how often you drive, eventually you can drive without thinking. Eventually you become aware of your environment without specifically telling yourself to be aware of your environment. Although, you have bad drivers. Some people should be more aware than they are, but you get what I'm saying, right? In the beginning, it's going to be very weird, very scary, very uncomfortable. But you expose yourself enough to that discomfort, it becomes second nature after a while. That's where you want to be. Expose yourself to discomfort enough to the point where it becomes second nature. You become comfortable with the discomfort. Okay, let's quickly go through this. Keep looking at the other page because I redid the order of my examples. So example 1 was this guy. So I want you to do 2 things. First, I want you to find the inverse, and then I want you to sketch that. In like 5 minutes. Okay, so how do you find an inverse? Switch x and y, solve for y, right? So x log to base 3, y minus 1 minus 2. And now we want to solve for y. So let's do it over here. So of course, I want to isolate this guy, right? The y. In order to isolate the y, I need to isolate the y minus 1. In order to isolate the y minus 1, I need to isolate the logarithm. So my first step is to get rid of that 2. Okay, how do I get the y outside the logarithm? Well, a law of logarithms, right? 3 raised to this power gives me that number. I'll show you another way to think about this maneuver next time. So in other words, now my y is just going to be 1 plus 3x plus 2. There's another way I can think about this. This is 3 squared times 3 to the x by the exponential rules. So it's 1 plus 9 times 3 to the x. In other words, I take the 3 to the x graph, stretch it vertically by 9, and then shift it up by 1. So I kind of already know what that graph is going to look like. It's going to be 1. And another way you could do it, again, of course, you could actually compare this to the answer we got in part A. It's going to be that reflection. So if you want to figure out where it actually hit this intercept, where did we hit the other intercept before? Was it at 10?
10. Yeah.
Right, this is going to be at 10. Let me give you guys some things to try over spring break, kind of where we're going. So redo the last example here, and as well as start looking into how to do these guys.
Just practice.
Oh,
But we have them. The 22nd episode.
Which we'll go over next time I see you, which is going to be after spring break.
the homework?
Yeah, they're short.
Oh, okay. Like, 3
That's
points,
it.
4?
It's the 3.3.
Simplify. Simplify all those. Oh, I actually missed the ln of this thing. So know how to simplify expressions, and again, be aware that simplifying an expression and solving an equation are two different maneuvers. Do not mix up your maneuvers. So I want you to solve these equations. Last one. We'll kill those problems next time.
Excuse me, Professor?
Yes.
I wanted to take a picture. Sorry.
Yeah, ain't nobody got time to write all that.